This is meant for the students. The lecture e-content is meant for student usage. And the topic is from course name Physiology 2. Topic is Mechanism of Hearing. Topic delivered by Dr. Henry Bharadwaj, MD, Professor, Department of Physiology, Faculty of Medicine, Sri Lakshmi Narayana Institute of Medical Sciences, Puducherry, affiliated under Bharat Institute of Higher Education and Research, Chennai. To know the mechanism of hearing, it is essential to know the functional anatomy of the ear, which includes the outer ear. The functional anatomy includes the outer ear, the middle ear, and the inner ear. The outer ear includes the external acoustic meatus and the auditory canal. And the tympanic membrane separates the external ear from the middle ear. The middle ear, actually, the vital part is the oval window through which there is a perilymph, and that is sealed by the foot plate of the stapes. And the sealing is done by the soft tissue of the foot plate of stapes. The foot plate of stapes is connected to the vibrating tympanic membrane by the two other small bones, that is the malleus and incus. Stapes is otherwise known as stirrup. It is known as stirrup, and this is the foot plate of the stapes. And there is this is called the ossicular chain. Malleus, incus, and stapes is known as the ossicular chain. And to prevent the damage from loud sounds, there are two small muscles in the middle ear, the tensor tympani and the stapedius muscle, which cause dampening of the effects of the sound waves, which are compression and rarefaction. So with every compression and rarefaction, the tympanic membrane moves, causes movement in the malleus, incus, and stapes. The actual name for the stapes is stirrup. They put on the horse, and the foot plate, just above the foot plate, the foot goes in. But here, the foot plate is used for sealing the wrong window so that the perilymph is kept in place, and movement of this foot plate of stapes causes movement of the foot plate of the stapes causes compression and rarefaction in the perilymph and endolymph in the internal ear of the cochlea. The scala tympani and scala vestibuli have the perilymph, and the scala media has the endolymph. And in the scala media are the receptors for hearing. There's the hair cells with stereocilia. Movement of these stereocilia causes depolarization of the hair cells. And this is the eardrum is 17 times area-wise, 17 times more than the oval window. And vibration of the tympanic membrane or the eardrum due to vibration, rarefaction, and compression of air in the auditory canal and external auditory meatus is transmitted to the eardrum or the tympanic membrane, which vibrates. It is 17 times to 1, the ratio between the tympanic membrane and the oval window. is 17 times to 1, and this is essential in impedance matching. Impedance comes from the fluid in the perilymph, the endolymph, and the basilar membrane vibrating, and the stereocilia also may produce micro-mini impedance matching. Next slide shows the cross section showing the scala vestibuli, scala tympani, and the organ of Corti, which contains the hair cells. And the hair cells, the stereocilia of the hair cells are embedded in the pectoral membrane. Stria vascularis is blood vessels that secrete into the scala media, the endolymph, which is rich in potassium. And the scala vestibuli also has perilymph and is responsible for the displacement of the basilar membrane and distortion of the stereocilia of the hair cells. Scala tympani supports the basilar membrane, which is also has, scala tympani also has scala tympani also has perilymph. This is the basilar membrane, which holds the receptors for hearing the hair cells, and they are called collectively the organ of Corti. This is the cochlea rolled out. The 2.5 times rounded cochlea is stretched out, and this is the stapes, which is responsible for conveying the compression and rarefaction of the air via the tympanic membrane and via the various increscent stapes, ossicles, the ossicular chain of the middle ear. And this is responsible. Depending on the frequency of the sound, the hair cells get distorted, and the dissipation of this rarefaction and compression in the cochlea is disseminated by the round window. This is the scala tympani, this is the basilar membrane, this is the helicotremon, where the scala vestibuli and scala tympani communicate. It is here somewhere that you have the stria vascularis somewhere here inside. Now, high frequency sounds, the displacement is nearer to the modulus, high frequency sounds, the displacement is nearer to the modulus, so the oval window and the round window, and the displacement is of the basilar membrane is towards the structure, the oval window, round window, and modulus. And this displacement occurs, the hair cells have the stereocilia, the hair-like processes on their upper surface, which is bathed by endolymph, and this displacement is called the traveling wave theory of sound. Then you have the medium frequency sound, where the displacement of the basilar membrane is in the middle of the cochlea, this is the rolled out cochlea, and the hair cells over here get displaced maximally, and the stereocilia move well. The stereocilia move well. So the stereocilia move well, and this is responsible for the opening of potassium channels, because the endolymph is rich in potassium, which comes from the stria vascularis, and the whole endolin comes in this stria vascularis, and it is rich in potassium. This potassium influx into the hair cell process, into the stereocilia of the hair cell causes depolarization. This is the medium. This is the low frequency. Low frequency sounds, the displacement of the vesicular membrane is more towards the helicotremor or the modulus. So this one is the displacement, and it occurs and this, if this much the displacement occurs here, it will be detected as a low frequency sound. High frequency sound is a high pitched sound, female voice, and low frequency sound is mostly a male voice, or this husky whisper. Yeah, this is to show particularly the hair cells, stereocilia, attached to the pectoral membrane and the outer hair cells. Here, this is the hair cells, and this is another hair cell, the inner hair cell, which also has stereocilia. The basilar fiber, which gets displaced by the sound, by the traveling wave in the perilymph and endolymph. Yeah, this is the basilar fiber, and this is the hair cell with the stereocilia. It is embedded in the tectorial membrane. Yes. So basilar membrane by its displacement moves up and down, and the reticular lamina, which holds the hair cells, and the stereocilia of the hair cells are fixed to the tectorial membrane. And the reticular lamina moves from side to side, and the basilar fiber moves up and down. These are the rods of the cocci. This is the modulus. This is the stereocilia, which is it's called top link protein. It's red one, and it passes through the tip of the stereocilia, and this link protein connects the potassium channels in the tip of the stereocilia, and with the movement of the endolymph, also the perilymph, the stereocilia get slanted, and the smaller stereocilia move towards the taller stereocilia, which were earlier called tenocilia. But nowadays, the term appears to have been given up, and they call it simply, all of them are called stereocilia. What happens is that when this movement takes place due to displacement of the basilar membrane, and the basilar membrane gets displaced because of the conduction of the compression and rarefaction of the perilymph and endolymph, thanks to the same thing happening in the air outside and outside the ear and in the outer ear. And tympanic membrane vibrates, and this is conducted to the foot plate of the stapes by the ossicular chain. Now, potassium is rich in the stereocilia, and it moves into the hair cells, and this causes depolarization of hair cells shown exceedingly well in this diagram. There's depolarization, and what happens is that calcium enters through voltage-gated calcium channels. Because of the depolarization, the calcium channels open, and the uh, the neurotransmitter, which is in the cycles, due to the calcium, it gets exocytosed and released into the interstitium of the interstitial fluid. And this neurotransmitter is nothing but glutamate, which opens up sodium channels in the nerve, in the afferent neuron, and causes action potential. Yes. So this action potential is conducted via the spiral ganglion and goes via the cochlear division of the vestibular-cochlear nerve. Vestibular nerve supplies, the vestibular nerve supplies the uh, semicircular canals, which are there in each of three planes, and the saccule, saccule, which detects acceleration in the horizontal plane, and the utricle, which detects acceleration in the vertical plane. Okay. This is old age type of neural deafness. Old age type of neural deafness, wherein the the loss of air conduction and bone conduction are decreased to 40% less decibel. So the both are decreased, and but the air conduction is decreased more. Bone conduction is also decreased. Bone conduction, air conduction is decreased more, and bone conduction is decreased less. And it should be appreciated. And when compared to the next audiogram for middle ear issues causing deafness, this is frequency 1. Normally, frequency 20 cycles per second is more than is the range is 20 cycles per second to 20,000 cycles per second. The compression and rarefaction. Now, that is given over here and it is directed, and it occurs that bone conduction is less and air conduction dips only after 2000 cycles, frequency of 2000 cycles per second. This is 4000 cycles. This is with old age type where the nerve is involved. So nerve, neural deafness, sensory neural deafness. Sensory neural deafness. This is with conduction deafness resulting from middle ear sclerosis. What happens here is there's an infection of the middle ear occurs, and it's called otitis media, and there is inflammation, and the response is sclerosis or fibrosis of the contents of the middle ear. So what is affected is that tympanic membrane can get perforated, and so it won't participate much in transmission of the compression and rarefaction. And the Malleus incursus stapes can get fused, and the most important thing is that the stapes gets fused with the oval window because it's uh, connection, soft tissue connection with the oval window gets fibrosed, And this occurs mainly in the antibiotic gentamicin. So here you can see that the frequency is 125, and earlier with sensory neural deafness, as an old age, it started with a frequency of 1 cycles per second, and recording the stimulus was given for up to 8,000 cycles per second. So this is in old age, sensory neural deafness. It means the nerve is involved. Audiogram of air conduction deafness resulting from middle ear sclerosis. So here the recording starts at 125. So at higher frequency, the air conduction is heard better because the higher frequency, the movement occurs better of the motor parts of the middle ear and the inner ear. The inner ear movable parts include the perilymph, the endolum, so the basilar membrane, and the stereocilia, which move towards the longer stereocilia to open up the potassium channel and cause influx of potassium. To cause influx of potassium. So we could go back, yes, to see that influx of potassium occurs here when the movable part of the hair cell, that is the stereocilia, there is stereocilia move towards the tallest of the stereocilia. This is the direction of movement, and this is the tip link protein that is connected to the potassium channel in each one of the stereocilia. So we have the potassium channel, and potassium influx occurs into the hair cells. Potassium influx is a potassium is a cation and brings about depolarization of the hair cell, and the depolarization opens up voltage gated calcium channels, and these calcium channels, just like in the excitable tissue, particularly the nerve, the action potential, when it reaches the presynaptic tuft, it causes opening of the uh, calcium channel, and calcium influx occurs, and it brings about the exocytosis of uh, the exocytosis of the content of the cycles, which is a neurotransmitter. This neurotransmitter is exocytosed by fusion exocytosis complex into the glutamate, into the interstitial fluid, intercellular fluid, the one cell being the hair cell, the receptor for hearing, and the other one being the neurons, the afferent neuron. And this glutamate opens up sodium channels to cause depolarization and impulse generation in the initial segment of the afferent nerve. And this moves down to the spiral ganglia, and it causes impulse traffic in the cochlear division of the vestibulocochlear nerve, and uh, the cochlea, the vestibular part of the vestibulocochlear nerve supplies the semicircular canals. The semicircular canals are in 3 planes, and each one of these planes are provide circular acceleration. provide circular acceleration. And they cause maintenance of balance. Then there is the utricle and the saccule. The saccule causes, it gets stimulated, the hair cells in the saccule get stimulated by horizontal acceleration, the utricle by vertical half, or maybe the other way around, but the saccule gets stimulated by horizontal, by vertical acceleration, and the utricle by horizontal acceleration. So this is the potassium influx of the circulation. Yeah. This is where the potassium influx occurs, and it causes movement of the reticular lamina, which causes movement of the stereocilia towards the right, towards the thallus of the stereocilia, and it causes potassium influx. And this potassium causes depolarization of the hair cell. And there are, it's not shown, the neuron, the afferent neuron that comes from the hair, that is near the hair cell, only with the interstitial fluid in between, and this neurotransmitter glutamate is released from the hair cell by fusion exocytosis complex, thanks to calcium, thanks to the presence of calcium. This reaches, the glutamate reaches the interstitium and causes depolarization of the neuron at the initial segment where there are a lot of sodium channels, and this causes a generation of impulses, leading to impulse traffic in the afferent nerve, and impulse traffic to the cochlear division of the vestibulocochlear nerve. Here brought about by movement of the perilymph and the endolymph, causing distortion, movement of the stereocilia towards the one side, towards the taller stereocilia, and causing entry of potassium, which causes depolarization, and causes depolarization, and causes opening of voltage-gated calcium channels. So there's a calcium influx, which causes fusion exocytosis of the neurotransmitter containing the cell. This basilar membrane, it's worth mentioning, moves up and down thanks to the displacement caused by the footplace of stapes in the perilymph, and that is connected to the endolymph, and the endolymph causes the displacement, up and down displacement of the displacement. Here, the reticular lamina moves side to side and causes this displacement. So this is traveling wave theory of sound. This is the hinge for the traveling wave theory of sound. And this is the tectorial membrane, which is embedded in the stereocilia.